Hello friends, in this video lecture we are going to discuss about the performance parameters of power amplifier. So first performance parameter of an amplifier is the amplifier efficiency. It is defined as it is a ratio of average AC power delivered to the load to average DC power drawn by the circuit. It is given as eta equal to P0 AC divided by P in DC. It has a drawback of that it does not consider RF input power. So other one efficiency is used for the better measurement of amplifier efficiency is power added efficiency. In this efficiency, it accounts RF input power. Therefore, the efficiency of amplifier is modified by using the equation eta PAE equal to P0 AC minus P in EC divided by P in DC. So it can also written as eta PA equal to 1 minus 1 upon G eta, where G is a amplifier gain given as G equal to P0 AC by P in EC. So this is the difference between power and efficiency and amplifier efficiency in terms of inclusion of RF input power. Next, what is a distortion? So know that at a high power, amplifier acts as a non-linear device. So because of non-linear, distortion occurs at the output of amplifier. So distortion is the change in output waveshape from the input waveshape of an amplifier. It is in terms of phase and amplitude. At the output of transistor amplifier, some part of the power is dissipated in terms of heat. The amount of power dissipated in terms of heat, that ability can be determined with the help of power dissipation capability. That is the ability of a power amplifier to dissipate heat. Next is an important point, that is the 1 dB compression point. The figure shows the graph of output power versus input power, shows two graphs. Dotted line shows a linear graph and the dark line shows a non-linear graph. So linear and a non-linear graph follows the same path at a certain point. So after that point, both are deviate to each other. That deviation is represented in terms of a 1 dB compression point. So it is the output power level at which the gain decreases by 1 dB from its desired value. So meaning is that generally our requirement that the output should follow the input with respect to a linear scale. So what happens at a high power, it follows a non-linearity. So 1 dB compression point is a point at which the gain decreases by a 1 dB. So this is the gain decreases by a 1 dB from its desired value. When an amplifier reaches its 1 dB, at that point it goes into compression and becomes a non-linear device. So it produces distortion, harmonics and intermodulation products. Therefore, our requirement is that the amplifier should always be operated below the compression point. In short, 1 dB compression point is very important at the time of the designing of the power amplifier, because above 1 dB compression point, device acts as a non-linear, which causes a distortion and a harmonics, whereas below the 1 dB compression point, it acts as a linear device. The range of this linearity is represented by a dynamic range. Dynamic range is a range of the output power during which the device behaves as a linear device. So this is a range during which device behaves as a linear device. Whereas P0 MDS and P0 MAS is given as P0 MDS, P in MDS is a minimum detectable output input signal power, whereas P0 MAS and P in MAS is represented as maximum allowable output input signal power. So means the dynamic range is calculated in between P0 MDS to P0 MAS. 1 dB compression point is given in terms of dB by using a formula G1 dB. It is equal to G dB minus 1 dB, where G dB is amplifier gain, minus 1 dB, where J1 dB is also represented as output power at 1 dB point divided by input power at a 1 dB point. It can be represented in terms of dBm as G1 dB equal to P01 dB in terms of dBm minus P in 1 dB in terms of dBm. This is a formula is used to calculate 1 dB compression gain. Generally, small signals are characterized by using the help of scattering parameters. But these scattering parameters are not suitable for large power signals. So, large power signals are characterized by using a load pull contours. So, these are load pull contours are nothing but the output power are plotted on the gamma L plane of a Smith chart. These are constant output power as a function of output, that is load reflection coefficient. If you see here, these contours are not a perfect circle because of non-linearity. So in short, load pull contours are used to determine large signal behavior of an amplifier, whereas small signal behavior is determined with the help of scattering parameters. And these load pull contours is provided by manufacturer as a data sheet. So it can be useful at the time of designing high power amplifiers. So see the difference between small signal S parameters and load pull contours. So S parameter used to measure small signal source and load impedances, that is a low power signal. Whereas load pull contours used to measure large signal source and load impedance, that is a high power signals. Whereas S parameter do not measures output power, whereas load pull contours measures output power. S parameters are valued for small signal linear devices, meaning that it is only applicable for linear devices, whereas load pull contours can be used for linear as well as non-linear devices. S parameter used to design small signal class A amplifier, whereas load pull contours are to be used for designing of large signal class A, class B, class AB as well as class C amplifier. So this is the difference between S parameters and load pull contours. So thus we have seen the different performance parameters of power amplifier that can be used at the time of designing power amplifier. Thank you.